Well, it's a real pleasure to welcome Mark Haskins, who's going to give the first talk of this afternoon, and his title is Recent Progress in G2 Geometry.
Thank you very much, Claude. Thank you very much to the organizers for giving me the honor to speak here. I want to just start with just some personal things. So November 11th, 1995 was a very important day for me. That I was a student of Karen Uhlenbeck's in Austin, Texas, and Texas Geometry Topology Conference was going on. And that day, David Morrison from Duke came to visit. And, well, also Mike Anderson was talking there that day. But what stuck in my mind was David Morrison's talk. His talk was entitled Supersymmetric Maps and the Topology of Calabi-Yau Manifolds. And talking to him afterwards in collaboration with Karen, then he said, well, actually these things are related to calibrated geometry of Lawson and Harvey. And Karen, what we want you to do is prove some compactness theorem for special Lagrangians. And Karen said, I've stopped proving compactness theorems now, but this sounds like a great research problem for you, Mark. And ever since then calibrated geometry has been the main focus of my research. So, so I can tell you to the day on which I first discovered these beautiful objects, and so I want to thank Reese and Blaine for discovering this beautiful mathematics, which I've continued to think about for the last 15 years. So I would also like to thank Conan for the last talk, in which he talked a lot about G2 geometry. So there are various things that normally I would begin with, but which I will maybe go a little faster over than normally. There are two caveats compared, so I must have paid Conan a reasonable amount, but I didn't pay him quite enough. One is that he decides to use, for his fundamental 3 form, he uses capital omega. For me, capital omega is a holomorphic volume form, and the fundamental 3 form is phi, or phi sub 0. So that's one important thing. The second important thing is Conan told you lots of beautiful mathematics, but he also cheated. He cheated because he was happy with a G2 manifold being a manifold whose holonomy is contained in G2. I'm going to insist that it's a manifold with holonomy G2, and I'm going to use lots of things about manifolds with holonomy contained in G2, but in the end, it's a lot harder to find something with manifold with holonomy exactly G2, and that's what I want to talk about. So this is based on joint work with these collaborators, one of whom, Tommaso Pacini, is in the audience somewhere. And it's based on 2 long papers that appeared this summer on the archive. So it's about, I'm going to try and do in an hour what takes up 140 pages odd. So it's going to be a little bit compressed. Okay. So what was our basic goal? So our basic goal, again, was informed by calibrated geometry. So as I'm going to explain, then, we already learned from Conan's talk that on any G2 manifold, where you're even allowed to be just holonomy contained in G2, then there are these natural calibrated geometries, the associative 3-folds and the coassociative 4-folds. And, well, it's relatively hard to find compact G2 manifolds in the first place. But if you found them, then you can ask yourself, can you find associative submanifolds? And Conan was describing one way in which both associative and coassociatives come up. But, so what we were interested in doing was trying to find compact associative 3-folds in G2 manifolds that are rigid. So rigid meaning as an associative curve, there's no small deformations of it. So we succeeded in doing this, and so the motivation was this question in calibrated geometry. But in doing so, we discovered various other things, and I want to describe those things as well today. So more or less, in order to be able to do this, then we had to find a lot more new non-compact Calabi-Yau threefolds. I'll try and explain why this is crucial later. So once we could do that, then we could construct lots of new compact G2 manifolds, many of which will contain rigid associative threefolds. But then what we also realized was, so typically, there are a few two known constructions of compact G2 manifolds. In that, you start with some, say, the simplest case, you start with some singular space, do some kind of resolution procedure, and show that that space admits a holonomy G2 metric. But if someone says, well, can you tell me which 7 manifold that is, then you're probably a bit stuck. You could say, well, I know it's simply connected, and I know its Betti numbers are this, but I'm not even sure in general about its integral cohomology, and usually I don't know its diffeomorphism type. So there wasn't a single compact G2 manifold where you could say, it lives on this 7 manifold. So one of the things that we were able to do was to actually show that for a large class of the G2 manifolds we can construct, then we completely identify what the diffeomorphism type is. So one immediate sort of byproduct of that is it turns out that you can start with, I'm going to explain how we do this, but you can start with what look like 2 completely different presentations of the same 7 manifold, and nonetheless find that both of those presentations allow you to find G2 metrics. And also that sometimes they allow you to find rigid associative threefolds, and those rigid associative threefolds is different in different cases. So it kind of begs the question, and we're not really, the tools don't really exist to detect this at the moment, but it gives candidates for G2 metrics on the same 7 manifold that may or may not belong to the same connected component of the space of all G2 metrics. So certainly the way that they arise, there's no obvious link between them. So then there's a final thing which I probably won't have time to stress today, but there are, by analogy with some sort of geometric transitions for Calabi-Yau metrics, then there are something similar going on in the G2 world. So the goal of the talk is to try and explain at least some of those things, and hopefully at the end to even try and exhibit some specific 7 manifolds where we can present them in different ways. So that's the plan. So let's just, since Conan has done such a good job, then I can focus on some particular things of interest. So everything comes from this fundamental 3 form, which remember is not called omega, it's called phi. So, or phi sub 0 since it's on Euclidean space. So what I want to do is Conan exploited the fact that there was a close link between Calabi-Yau geometry and G2 geometry, and I want to do the same thing. So this is sort of a recap of things that Conan already said. But so on R7 we have this fundamental 3 form, but I want to write it in this particular way that stresses its connection with geometry in 3 complex dimensions. So I split off one factor and have another C3. And on C3, I have this standard SU3 structure. So I have the Kähler form and the holomorphic 3 form. And out of it, then I construct a 3 form by dt wedge the 2 form plus the real part of the holomorphic volume form. So this is one way of writing the G2 form. And it makes clear now that if I look at the stabilizer of this R factor, then this will be exactly a copy of SU3 sitting inside of G2. So more generally, if I take a Calabi-Yau threefold, by which, say, I mean a manifold with holonomy SU3, if I take the product of that with a circle, then that's a 7 manifold with holonomy SU3 sitting inside of G2. So this was exactly what Conan was doing at the end of his talk. But as I said, I'm not content with that. That's not a G2 manifold for me. I really want something whose holonomy is the full G2. But we're going to use these manifolds with holonomy SU3 to achieve this goal. So also important will be to split off some more factors at some stage. So if instead of just splitting off a line, I split off this R3, then again, having coordinates on this R3 and the SU2 structure, omega I and omega, capital omega, writing it as omega j plus I omega k in sort of quaternionic language, then the three form I can think of as I've got the three coordinates here, and then I've got omega I, omega j, omega k, and then the x's. So we will, so again, this if I look at the same way, if I look at now the subgroup of G2 fixing this R3, then this formula makes clear that this is SU2 inside of G2. So these simple sort of linear algebra type observations will be important for later. So just to say, so for a G2 structure on a manifold, then this just means a three form that looks like this standard model at every point. So a G2 structure on an oriented 7 manifold is a three form, so that every point there's an oriented isomorphism between R7 with phi 0 and this given three form. So this makes it clear, if I just are doing things point-wise, that G2 structures on R7, those are parameterized by GL7 plus mod G2. So this is a 35-dimensional space. That's the same dimension as the whole of wedge 3. So in this case, what's important is that this means that this is an open condition. So small perturbations of a G2 structure are again G2 structures. So this is important for the kind of setup of trying to actually find G2 holonomy metrics. So as Conan explained, then if I have a three form of this kind, then it actually automatically determines a metric. The formula for doing that is cubic in the three form. So what I want to know is, if I've got a G2 structure, then it gives me a metric. When do I get a G2 holonomy metric out of it? So the lemma is the following. So at least, so you have some G2 structure phi. It determines a metric G, which depends on phi. You want to know, at the beginning, what we want to know is when is the holonomy a subgroup of G2? And then I will give the extra condition that we have the whole G2. So it's a subgroup of G2, and phi is the induced three form, is the same thing as asking that the three form be parallel for Levi-Civita with respect to the induced metric G, or it's the same thing as asking that this form be closed and co-closed. So you should remember here that this condition is linear in phi, But here we're using the Hodge star with respect to the metric induced by phi, but that's already nonlinear in phi, so the second condition is a nonlinear condition in phi. So because of the second condition, then we call this type of G2 structure a torsion-free G2 structure. And so if all I wanted was something whose holonomy was contained in G2, then I would be done, because I would have just taken a circle across a Calabi-Yau. But what I would like to know is under what additional conditions am I guaranteed not just to have inequality, this inclusion here, but equality. So if we want to know what kinds of 7 manifolds have G2 holonomy metrics on them, well, first they need to have a G2 structure. But that's easy enough to understand. That's a purely topological condition that it has a G2 structure if and only if it's orientable and spin. But so now suppose that it has a G2 structure that's torsion-free, then we know its holonomy is contained in G2. When do we get the whole G2? We get the whole G2 if and only if at least in the compact case, the fundamental group is finite. So in particular, in the previous case where we had S1 cross Calabi-Yau, then we had this reduction of holonomy. But if we don't have some splitting like that, then we'll be in good shape. So these are some necessary conditions for a manifold to admit metric of holonomy G2. There's another obvious condition, namely that its first Pontryagin class is non-zero. And the proof of this is just to use some elementary Chern-Weil theory and just the basic G2 representation theory. And the same kind of argument gives a little bit more information about the cohomology as well. But already this should say, well, suppose that I take a parallelizable 7 manifold, then it's certainly going to be orientable in spin, but it's never going to have a G2 holonomy metric on it because its first Pontryagin class is 0. So in some sense, at the moment, I mean, there are no canonical G2 holonomy 7 manifolds. The most obvious 7 manifolds that you think of are not going to admit G2 holonomy metrics.
Do we know anything about these classes where the holonomy is inside G2 but not just G2?
Sorry?
Do we know anything about item number 3, and the holonomy is inside G2? With the first Pontryagin class. Do we know anything about them? If the holonomy is inside G2?
Well, so yeah, I think some similar statements are known for Calabi-Yau threefolds. But I would have to think exactly what the statement is. So this suggests just sort of the germ of an idea for how to construct G2 holonomy metrics, and this is the only way to construct, the only known way to construct compact manifolds with G2 holonomy at the moment. So
I think you get an integral formula where you would be looking at P1 cup the
fundamental 3, yes.
Form, right?
Yes.
And then that has so if you look in Joyce's book, there's a nice formula. It basically measures the normal curvature. So
well, so in general, it's the difference of two terms. And then in the holonomy exactly G2 case, then you can show that one of those components is 0, and therefore this thing has a sign. But in general, it's the difference.
If the holonomy is contained in 2.
Yeah. So yes.
So
Yeah.
I think that you'd still conclude basically that it wasn't flat.
Yeah.
That this would be non-zero.
Yeah. I mean, you'd have to look at those two terms and check. So a potential strategy, and one that's the only one that we know how to make work, is first you try and find, so G2 holonomy metrics are rigid objects, but relatively rigid objects, but G2 structure is very flexible. So we want to use this more flexible setting. So we want to find, by hook or by crook, G2 structure with sufficiently small torsion. So sufficiently small torsion should mean, in torsion-free, it means the form is closed and co-closed. So we want something at least where the failure to be closed and co-closed is sufficiently small. And then we want to do it on a manifold with finite fundamental group, bearing in mind this here. So then the aim is, if we could find such a thing, then we attempt to perturb to a torsion-free G2 structure, but then we apply 2 and say, okay, well, torsion-free already means the holonomy is contained in G2. We'll get exactly G2 because of our topological assumption. So it's crucial to control some topology, namely the fundamental group, but the rest you don't need to control so much for the construction. So this approach was pioneered by Dominic Joyce, and in some sense, he answered to in a very in great generality, at least when the original background form is closed. So there was a lot of work involved in settling that, and that was one of Dominic's fundamental contributions. But given that, then it reduces the problem now to finding G2 structures or closed G2 structures with sufficiently small torsion. So there are basically 2 known ways of doing this, and both involve a sort of degeneration that, unlike if we compare life to the Calabi-Yau world, in the Calabi-Yau world we understand very well, thanks to, in the compact case, thanks to Yau's proof of the Calabi conjecture, and in the non-compact case, thanks to work of various people, but particularly Tian and Yau together. We understand very well how to find Kähler-Ricci flat metrics that are not close to any kind of obvious limit. In the G2 world, then all we can do is, well, G2 manifolds in particular are Ricci flat. There are various obvious ways that that Ricci flat metrics might degenerate. There are 2 simple ones to have in mind. One is where it starts to develop an orbifold singularity in codimension 4, and that was more or less what Dominic exploited. But the other, and arguably sort of geometrically simpler thing would be, well, you have a family of things where the diameter doesn't stay bounded. So you have a family of G2 metrics, and the diameter goes off to infinity, say. So then what naively you would expect is that it will break up into 2 pieces, which will become asymptotically cylindrical G2 manifolds. And then you would try and construct something close to that limit by cutting off bits of those and gluing them together. That sounds great, except it doesn't sound like it's any simpler to find asymptotically cylindrical G2 manifolds than to construct the original G2 manifold. So I'll come back to this in a moment and tell you what the sort of resolution of that is. So just now to remind ourselves, then, on R7 we had these fundamental 3 forms, the 3-form and the Hodge star. Both of these are more or less by definition G2 invariant and then calibrations. And as Conan explained, then the calibrated planes calibrated by the 3-form we call associative planes because they correspond to associative subalgebras of the octonions. So for example, in our splitting earlier, then the R3 that we wrote in this splitting is an associative 3-plane, and in fact the G2 acts transitively on the associative 3-plane, so you can think of this as a standard model. And well, so there are the co-associative planes also, which are less important for my talk. And because of the standard holonomy parallel tensor correspondence, then anytime I have a manifold with holonomy contained in G2, then I get parallel 3 and 4 forms modeled on these constant coefficient things. In particular, associative calibration exists on any G2 manifold. So in the same way that I described some relation between the extrinsic geometry, the Calabi-Yau and G2 geometry. Then we can also look at submanifolds, and this was already important in Conant's talk. So in particular, when I think of if I've got a Calabi-Yau threefold, and I take its product with S1, recall that had holonomy SU3 inside of G2. But I could still talk about associative submanifolds of this. And some obvious associative submanifolds arise as following. If I take a circle cross a two-dimensional surface inside of this, then this will be associative if and only if that surface is a holomorphic curve in the Calabi-Yau. So this was already mentioned in Conant's talk, but this is fundamental to being able to construct our associatives later on. Moreover, then the infinitesimal deformations of this sort of split associative actually correspond to infinitesimal deformations of this as a complex curve. So again, this will be important later on in that for a general associative, then I don't have very good control of the deformation theory. For complex curves, then, well, I have the whole of algebraic geometry at my disposal to help try and control some of this. And so in some cases, I'll be able to control the deformation theory of special associatives because they are linked to special curves. So there's a similar thing for co-associatives and special Lagrangians, but it's grayed out because it's less relevant for today. So what's the key to resolving this problem about the fact that it doesn't seem any easier to construct asymptotically cylindrical things than to construct the original compact G2s? So this was a suggestion by Simon Donaldson. So what he suggested was there is a way to go from Calabi-Yau geometry in 3 dimensions to genuine G2 holonomy manifolds, and I want to describe how it goes. So you want to construct asymptotically cylindrical Calabi-Yau threefolds. So as I indicated, then the technology for doing that does exist. So then you want to promote that somehow, not just to take a product with a circle and get a fake G2 manifold. You want something with holonomy G2. So what are you going to do? So you first have to understand how to construct these asymptotically cylindrical things. We'll return to that later. So then we do just take this product with a circle. So this gives us a non-compact asymptotically cylindrical manifold where the cross-section is a T2 cross a K3. And I want to take a pair of them and join them somehow. So I could just try and do a connect sum, but if I just did the straight connect sum, then what I would get would just be sort of an S1 cross something like Calabi-Yau, and then this would not have finite fundamental group, and this would not have a holonomy G2 metric on it. So what Simon's observation was well, we have a very special cross-section here, so we have this torus, and what I could just do is try and do this identification with a twist. So that's what corresponds to this twisted connect sum, and I will explain in more detail on the next slide exactly what that means. So then this twisted connect sum will be constructed in order to allow ourselves to find a manifold with finite fundamental group, but which still has a G2 structure with small torsion. If we can do that, then the analysis that Joyce already did will allow us to actually perturb it to torsion-free, and then the results will tell us, actually, this is what we need. So the key thing is what is this twisting here? So this was first carried out by Alexei Kovalev, in which case the asymptotically cylindrical Calabi-Yaus came from a certain type of threefold called Fano threefolds, and I will say a lot more about this. So to explain the twisting, then we need to go back to formula that we had before, sort of slightly modified. So on my 7 manifold that looked like a Calabi-Yau, an asymptotically cylindrical Calabi-Yau across a circle, then asymptotically the G2 structure becomes like this. So if I have a coordinate t on here, and then I have θ1 and θ2 for my T2 directions, and then I have the K3 directions. So I have this formula here, and where omega I, omega j, and omega k are this hyperkähler structure on each of the asymptotic hyperkähler K3s at the end. So what we want to do is we want to map the cross-section, map the ends to itself. So what we're going to do is we've got these 2 circles. We're going to exchange the 2 circles. So then we still need to get a well-defined G2 structure, so then we need to stare at this formula. And so we're doing like a connect sum, so we're still sending t to minus t with a shift. So if we switch these and send t to minus t, the first term is OK. But now we look here, we want to exchange θ1 and θ2, but that means we're going to have to exchange the roles of I and j. And similarly here, and then t, we have to send omega k to minus omega k. So what we need is we need to have a diffeomorphism of these 2 K3s, which does the following. It pulls back omega I on one to omega j on the other, vice versa, and k to minus k. So in particular, it is not a biholomorphism of K3s. And so constructing those hyperkähler rotations is somewhat non-trivial and is a major part of the construction. And as a slight health warning, then some parts of the original argument in Kovalev's paper are not correct there. So this is a relatively delicate thing. But
you could set it up so that if K was the reference complex structure, then it's just any holomorphic on K3. So I mean you're sending omega K on one side to minus omega K on the other side. So the map would be any holomorphic with respect to that complex structure. But is it set up so that
But I mean, we're going to be getting sort of a natural I just from this thing living inside of some other Fano, that's what's called I. And you don't really you only get to control that by moving stuff around in your Fano. So you don't get to dictate.
I see. But in the matching, would it be possible instead to just call the thing that one K, and then you'd have just a rotation in the canonical line bundle to get this I and J relation? I
mean, in general, certainly the K3s don't have to look anything similar. So one K3 in the Picard lattice could contain one kind of big sublattice, and the other one would contain a completely different one. So there's.
I see.
Okay. So to sort of review, then what we need to do to construct these so-called twisted connect sum G2 manifolds is first construct these asymptotically cylindrical Calabi-Yaus in the first place. So Kovalev used Fano threefolds to do this and built on previous analytic work of Tian and Yao. Then you need to find sufficient conditions for the existence of hyperkähler rotations between a pair of these asymptotic K3s that arise. But then once you've done, I'll come back to this. Once you've done 1 and 2, then the rest of it always works. So once you've done 1 and 2, then you can always glue the 7 manifold, the asymptotically cylindrical 7 manifolds that you get by crossing these things with a circle. And you can always glue them to get this almost G2 holonomy, and you can always perturb. So somewhat sort of surprisingly, then you've got this nonlinear PDE in 7 dimensions, which you've now reduced to two problems about complex projective threefolds. So let me just try and say some things about where you go looking for such asymptotically cylindrical Calabi-Yau threefolds. So it will turn out that it suffices to find a projective threefold where you have two smooth anti-canonical divisors that are K3 surfaces and that intersect transversally. So if you can do this, then those two divisors will intersect in a smooth curve. This is the base locus of this pencil. And then you blow up X, the original threefold, along this base locus, and you get a new projective threefold Z. And the point is then that the proper transforms of D and D prime are still smooth anti-canonical divisors on the new thing, Z. But now the pencil they determine really gives you a morphism to P1. So this thing now really fibers over P1. Previously it didn't because it had a base locus. And the generic smooth fiber is a smooth anti-canonical K3. And then what you do is you pick any of the smooth fibers and you remove it. So then the theorem is that any Z minus any such D admits asymptotically cylindrical Calabi-Yau metrics. And exponentially is in there to say that it approaches the product structure in an exponential way, and this is important in terms of controlling the error when you do the gluing. So the proof of this is, well, the original version is to take the work that Qian and Yao did, which shows that there is an asymptotically cylindrical Calabi-Yau metric, but it doesn't prove the exponential decay. Then there was an argument of Kovalev to get this exponential decay, but there's actually a Sobolev inequality used in his argument that is false in this setting, so then you have to give some corrections to that. In joint work with Hayo Hein and Johannes Nordstrom, then we also gave a simple direct proof where the existence at the beginning, you build in the exponentially asymptotic structure right away. So it gives a much more streamlined proof in this special case.
So to match the K3s, you have this complicated matching condition.
Yeah.
You actually have to construct things, I guess, in families. So
yes.
You sweep out an open set and a
So we're going to say a bit more about that. But yeah, so this will say, sort of, given any data, then I can construct things. But there's obviously variations that I could do here that, I had which fiber to remove. I certainly had that freedom. Probably the original X itself comes in a family. And I got to choose which pair of divisors to use to blow up as well. So clearly these things will come in families, and then in what we will need to understand fairly precisely what kinds of K3s arise in such families. So also an outgrowth of this work with Hein and Nordstrom was that actually all what we'll call asymptotically split Calabi-Yau threefolds do arise from this kind of construction. So asymptotically split really does mean that the cross-section at infinity was this product of S1 cross K3. That needn't be, the general asymptotically cylindrical Calabi-Yau need not split like that. If it does, then it comes from such a construction. So now, I said that Kovalev used Fano manifolds, so I want to say a little bit about Fano and a slight weakening of Fano, which turns out to be very useful. So I'm dealing with smooth things at the moment. So a smooth Kähler threefold being Fano means its anti-canonical bundle is ample or positive. For a weak Fano, then I want to weaken the positivity condition and have some kind of semi-positivity instead of positive. So the right condition there is that instead of being ample, it's so-called big and Neff. And what do those things mean? So if it was ample, then if I take the first Chern class of my line bundle, then and evaluate that on any holomorphic curve, that will be positive. For Neff, I just require that it's non-negative. Big means that, well, if it was ample, then when I start taking a high tensor power and look at how many holomorphic sections it grows as rapidly as possible. Big says the same is still true. So, so under the condition of Neff, then big is also equivalent just to a numerical criteria on C1 to the n. So morally, I'm going from this strictly positive sort of curvature case to a non-negative, sufficiently non-negative. So what are some basic important facts here that are very well known to algebraic geometers and less well known to the random differential geometer in the street? So probably everyone does know that for ample line bundles, we have very good vanishing theorems, namely the Kodaira vanishing theorems. So the original Kodaira vanishing theorems are stated this way. And if you state it this way, then they actually hold also for big and Neff line bundles. But in that case, it goes under the name Kalmata-Vivek vanishing. So partly using, in part using this, but using many other things, then one of the fundamental things that Shakurov showed in the early 80s was that if you take any smooth Fano threefold, then in fact a sufficiently generic anti-canonical divisor is a smooth K3 surface. So the smooth is really the key part. And then Miles Reed realized that, in fact, his argument, if you replace various uses of the Kodaira vanishing with Kalmata-Vivek vanishing, then Miles Reed realized this also works for weak Fano threefolds. So there's just a side remark there. So what this means in practice is that so we want to find these anti-canonically fibered threefolds, then well, we're going to be able to do that from almost any Fano or weak Fano. We just need to have enough. We just need to have enough anti-canonical. So we know we've always got at least one smooth one, but now we need a little bit extra to be able to get the base locus is smooth. So if what you want to do then is just to construct asymptotically cylindrical Calabi-Yau's, then essentially weak Fano already suffices. So Kovalev used Fano, but weak Fano actually suffices. So why is that helpful? So we generalize to weak Fanos. So first of all, there are many more weak Fanos than Fano threefold. So let me just quantify this. So the number of deformation Fano threefolds up to deformation are completely classified. There are 105 deformation families. This was established as an outgrowth of the minimum model program. There are at least hundreds of thousands of deformation classes of weak Fano threefolds. And the classification for those is not surprisingly still ongoing. So there's only because there are many more weak Fanos, then there are many more asymptotically cylindrical Calabi-Yau's you get this way. And hence, if you can do this matching, then you'll get lots more compact G2 manifolds also. And I should say, there's an abundance of compact Calabi-Yau threefolds, whereas previously we had a very small number of asymptotically cylindrical Calabi-Yau threefolds. So you could have asked, where are the missing asymptotically cylindrical Calabi-Yau's? Well, here at least is a lot more of them. These will all be exponentially decaying. Sorry? Different deformation families, yes. There are finitely many, yes. So there's a very general argument saying that smooth, weak Fanos in any dimension form a bounded family, but estimating what the size of that is, the bounds for that are sort of exponential in various things. So
there's a boundedness of degree estimate, but it's not effective.
Yeah. So I forget it's certainly Kolar and one of his students. So yeah, for weak Fano n faults, then this is known. If you want to allow Q Fano or something like this, then this is much more subtle.
True.
Yeah, it's true under some auxiliary extra hypotheses. So, but yeah, there are certainly finally many deformation families, but we have no idea of what the actual number is. But I can explain why we know there are at least these hundreds of thousands. But the other reason, and in fact the original reason that we were interested in it, returning to the associative submanifold point of view, was that, well, if I'm in a Fano threefold, then if I start with a compact holomorphic curve in the Fano, then that's going to intersect, because it's positive, it must intersect every anticanonical divisor. So in particular, if I start with a holomorphic curve, and then I take away, well, I first have to blow up and then take away a divisor, then this holomorphic curve is going to hit that divisor. So this holomorphic curve is going to go off to infinity in my asymptotically cylindrical thing. On the other hand, in a weak Fano threefold, then there are some special curves that will not meet anticanonical divisors. So then what I can try and do is, well, I can take that curve, take the product with a circle, that's give me an associative in the model thing, and then I want to see if I can perturb it. But it's a nice compact thing that stays away from where I'm doing the gluing, so I should be in good shape. So in particular, if I can find, say, a curve that's a smooth, rigid P1, then if I use this to build a G2 manifold via the twisted connect sum, then each of those rigid P1s is going to turn into a rigid associative submanifold of topology S1 cross S2. So to summarize, then, so weak Fano is already enough to construct asymptotically cylindrical Calabi-Yaos, but to get G2 manifolds, we need to be able to do more. We need to do this matching. So to do the matching, we have to do this hyperkähler rotation. And I can only sort of explain sketchily what goes on here. But roughly what goes on is that we will need to understand, as Claude was suggesting, what sorts of K3s arise as we vary various, the sort of degrees of freedom we have available to us. So we certainly get to vary the choice of the original divisor, and we get to choose the weak Fano within its deformation class. And then we want to know what kinds of K3s do we see. So then that means that we need some good deformation theory for such pairs. And this is a bit technical, and in the Fano case, then this was sort of treated by hand in Kovalev's paper, or there's a paper of Beauville doing this sort of more algebra geometrically. But when you go from, you find out that this deformation theory uses various vanishing theorems, and that are true in a Fano, but are not true in a general weak Fano. So what you need is an intermediate notion that's significantly weaker than Fano, but a bit stronger than weak Fano. And this is what the assumption is. It probably won't make too much sense to non-experts, but I'll just tell you what the punchline is. So a weak Fano threefold, then there's a natural singular model of it called its anticanonical model, which will be a singular Fano threefold. And then there's a natural morphism to its anticanonical model, and it will contract some things. So this will be a semi-Fano if this map is so-called semi-small, which in this case just means it's allowed to contract some divisors to curves or curves to points, but it's not allowed to contract divisors to points. And the reason why this is important is that the deformation theory of the pair is well behaved when this thing is semi-Fano. And the basic reason is that there are slightly stronger cohomology vanishing theorems that are true in this semi-Fano case than in the weak Fano case.
What do you mean by the well?
Well, I could explain afterwards, but it well behaved enough that the same techniques that allow you to work in the Fano world still work. I mean, it will be a smooth stack. Sorry? It's so we're also interested in the map to D, and so that's the part where so we're interested in the what happens when we look at the map from X, D to D, and it's needed there. So you have enough vanishing for the smoothness from this, but to understand D, then you need a bit more. So the upshot is weak Fano is enough to get your Calabi-Yaos, but if you need to be able to match, you need a bit more, and the most general class for which things seem to be sort of under control for general reasons is this class of semi-Fano threefolds. So once you can do this, then you can construct the compact G2 manifolds. So an immediate outgrowth of this is then that there are many topological types of compact G2 manifold that contain rigid associative curves that look like S1 cross S2. So in terms of associative submanifolds in a genuine G2 manifold where we can actually prove that they're rigid, then these seem to be the first examples. In Joyce, then there are some obvious associative submanifolds. It looks like they should be rigid, but I don't think one could actually prove that because of the way they were constructed. So as I said, then in general, the infinitesimal deformations correspond to harmonic spinors. So you have an index 0 problem, but you don't have a kernel problem, and in general, the deformation theory might be obstructed, and you don't, in general, have a good way to control deformations for a random associative threefold. Because these correspond to these rigid holomorphic curves, then we have much better control.
How do you know that they are different than Joyce's examples?
Well, so I'll say something more about the topology later, and so then that will become clearer.
Too many of them topologically. You can make a whole lot and
We could,
a small.
well, also basically, there's maybe one example of Dominic's which has B2 being 0, whereas we have maybe 50 million. I'm not saying they're all 50 million topologically distinct, but there are different matching pairs, all of which have B2 as 0. So none of those. Well, we do a lot more than just calculate the Betti numbers. In many cases, we tell you it's this 7 manifold. Whereas essentially, in Dominic's case, you could never tell me which 7 manifold it was because the class, well, you didn't even understand the integral cohomology. But then certainly they're not too connected, and then just at the moment, then the tools we have in smooth 7-dimensional topology are not very good and are not sufficiently good to give a nice algorithm for recognizing which 7 manifold you have. But if you're too connected, then such tools do exist.
So you can recognize that they're homeomorphic, they still might not be diffeomorphic.
So I don't think you even have good tools to recognize homeomorphism type or so there's something that we're in discussion with sort of people who are expert in this. So even if you replace two connected with simply connected and say the second homotopy group is Z or a finite cyclic, then that's still not known currently. But there's a guess what the answer should be, but that's not proven yet. So except one example, all of Dominic's examples have some obvious reason to have B2 being non-zero, basically because of the way he constructs things by resolutions. So just to make sure we understand why these associatives, why we're getting these rigid associatives. So we took this compact holomorphic curve in X that didn't meet the anti-canonical divisor. So that meant we still got a compact holomorphic curve in Z minus D. We took the product of that with a circle. That was compact associative in here. More or less by the way we constructed it, this thing is going to be rigid in many cases. So then this will be a rigid associative in here. And then now we're making a small perturbation of this because this is staying away from the end. And so we'll get a rigid associative as a result. So the analysis here is rather straightforward. And what you had to do was, the price you'd had to pay was to do some more algebraic geometry earlier on. So just to give some examples, then maybe the simplest example is to start with, say, so if I had a quartic threefold, a smooth quartic threefold would give me a smooth Fano threefold, but instead I look at something that's mildly singular with a special form. Namely, I look at something that contains a projective plane, and then I try to resolve it. So if it contains a projective plane, so I could think of it the following way. My equation I think of as having x0 times some cubic, x1 times some other cubic being 0. So then I think of the restriction to understand the singular points. I think of the restriction of this to the plane. So that gives me a pair of plane cubics. And so then we know that they intersect in 9, in general, distinct points. And then those 9 points will be singularities of this quartic threefold. And they will be the simplest sort of singularities, the ordinary double point singularity. So a quadric cone analytically, a quadric cone in C4. And then if I blow up the plane on which all of these things lie, then I will get a projective small resolution of this. And each of those 9 singular points gets replaced by a rigid P1. So a P1 with normal bundle O minus 1 plus O minus 1. So in this case, then I get these 9 rigid rational curves, and then those will give rise to 9 associatives if I use it on one side of my construction. So there's a slightly more complicated example here. Let me just skip that and then maybe end by giving some indication of the fact that there are a lot more. So if I look at smooth toric Fano threefolds, there are exactly 18 of those. On the other hand, if I look at semi-Fanos, then there are over 400,000 deformation types of these. So, and if you want things that have rigid P1s, then there are at least 1,000 of those. So roughly, what's going on here? So you start with your toric semi-Fano. Then again, you think of its anti-canonical model. This is some mildly singular toric Fano threefold. Mildly singular meaning this. And so those are completely classified in terms of some combinatorial objects, these reflexive polytopes. So Kreutzer and Scark classified those things by a computer sort of search algorithm. So there are 4,319 of those. These are the singular things. And then every one of those admits at least one projective Kreppmann resolution. So anytime you find such a projective Kreppmann resolution, it's going to be a weak Fano threefold. You want to recognize which ones are semi-Fanos. Well, that cuts down these to 899. But most of them actually have many different projective Kreppmann resolutions. And then this is something that you can enumerate kind of combinatorially. And so this is what we did with Coates and Kasparich. And so a Fano threefold, a toric Fano threefold is automatically rigid, but a toric semi-Fano is not automatically rigid, but again, it's something you can determine from the polytope. And so this is what leads to these estimates here. And then just the final slide. So using these toric things, then already you will get over 50 million matching pairs that give rise to two connected G2 manifolds. So basically, what you do is you take one pair to correspond to something of a toric type, and then something else that's of relatively low rank, low Picard rank, and then you now need to do this matching. The matching works sort of whenever you can arrange some lattice embeddings. And so you need to do a little bit of arithmetic to know something about some lattices and some discriminant groups. But basically, if you understand this, you find that over half of the toric semi-Fanos can be matched to any Fano threefold as long as its Picard rank is not bigger than 2. And then you look at the classification for those things, and there are already a couple hundred of those things. So now you take 250,000 times 200, and this is your 50 million. So let me stop there, and I can answer any questions.
When you're carrying out these small resolutions, presumably there are usually a lot of small resolutions that are not projected. I mean,
yes.
Is that part in enumerating which ones are projected and which ones are still?
So no, this is a serious problem. So I mean, for example, suppose that I had taken a quartic that had fewer than 9 nodes, then it turns out none of those things ever have a projective small resolution. And if I have 9 nodes, then they have a projective small resolution if and only if the nodes live on some projective plane. On the other hand, for the toric things, then it's relatively straightforward in that, first of all, I enumerate all possible Kreppmann resolutions, and then there's a general criteria to understand, I've got some fan, and then when does this correspond to something projective? So this is something that, I mean, in principle, you could look at it by hand, but it's actually easy enough to program also. So what we do is first we go through the list, we find which ones correspond to semi-Fanos, then we enumerate all possible resolutions, then we rule out the ones that are not projective, but then there's also the polytope will in general have some discrete symmetries, and those will permute the small resolutions. So then those are isomorphic resolutions. So you also need to mod out by that. And then similarly, in order to make the statements about the deformation types, if I didn't know that my thing was rigid, then, well, maybe this thing deformed to something else. But you can check rigidity directly from the geometry of the polytope. That goes back more or less to the original, well, you can compute what H0 is, and then you know what H1 minus H0 is, because there's some vanishing theorems. And so then H0 you can compute from the polytope.
Other questions?
So you say 50 million matching pairs now. How many distinct G2 topological types of G2 manifolds do you get from
Right. So had I gone slightly faster, I would have said. So basically, there cannot be more than roughly of the order of 10,000 diffeomorphism types that are obtained this way. So there's a huge redundancy in this. So there are all kinds of different ways of finding the same seven-manifold, but from a completely different presentation. Where if we just looked at it, there's no obvious way to see those are the same seven-manifold. We really have to use the classification of simply connected, two connected seven-manifolds.
So 10,000, but the choice of homework in the 100 choices.
So there's definitely more. I'm saying there's an upper bound in order to actually to know exactly how many kinds. Then, well, there are basically two things that you will need. One is to compute. So there's only one Betti number available to us, B3. That's easy to compute. You need to check whether or not there's any torsion in H4. In good cases, there's none. Otherwise, there's some other algebraic gadget that exists. The other thing you need to compute is the first Pontryagin class. And it turns out any twisted connect sum has very limited possible range of so you've got a integral element in some module, some Z module. All you really care about is how divisible it is. So because it's a spin manifold, it's automatically divisible by 4. But then because it's a twisted connect sum, then P1 always divides 48. So P1 is always in this narrow range there. And you have to figure out which one it is. And to do that, you need to look at the two sides. And then P1 of the G2 manifold will be related to the second Chern class of the two sides. And then you need to figure out the divisibility of the second Chern class of the sides, and then take the greatest common divisor of those in the simplest case. So you can do it in many cases, but on the other hand, precisely because it's always divisible by 4 and a divisor of 48, then there's always at most these ambiguous things. And then if you know that, then it turns out that classifies your seven-manifold up to almost diffeomorphism, where almost diffeomorphism means possibly connect summing with an exotic sphere might change things. But again, there are most 28 of those, and in many of these cases, knowing something about the P1 says not so much of that can happen. So combining all of that gives this 10,000. The smallest that I know is 31. So if you allow yourself to construct things that are not too connected, then you can trade some B2 for B3. So then you can make B3 smaller by increasing B2.
What's the fundamental proof of the?
It's always trivial in these cases.
Did I understand there's a bound on P1 wedge star P1?
P1 is a P1 wedge, the 3 form. Yeah, the integral of that is well, that's basically the L2 norm of the curvature. Well,
in this.
yeah. But I don't know that so for twisted connect sums, then, the other thing I should say is, so there's how do you get two connected seven manifolds? What's the model you should have in mind? Well, take any 3-sphere bundle over S4. That's always a two connected seven manifold. Then if you make the right Euler number for it, then it will have, what I want to say? Well, all I'm going to say is basically you've got the Euler number, and you've also got what Pontryagin class it can be. And for sphere bundles, then you could have any multiple of 4 as the greatest divisor of P1. So then you could take this and now connect some with any number of copies of S3 cross S4, and then also connect some with any homotopy 7 sphere. So that's what any 2 connected 7 manifold looks like that. Some circle, so some sphere bundle. So this was essentially an outgrowth of the work of Terry Wall, but it was one of his students, Wilkins, who did it except in some very special case where there was 2 torsion and then some extra, some algebraic gadget is more complicated than they originally thought, and that wasn't quite figured out until 2003 or something. So it's semi-classical. But replace that with simply connected and say pi 2 being z, and we still don't know. But already you could just have an S2 cross S5, and so it already becomes more complicated, and maybe there are Massey products around, and
how necessary is the exponential decay aspect of exponential progress? That is, to do maybe like a nonlinear decay or other types of decay and still do this type of construction?
well, you can always arrange to have exponential decay. So so it is used in the argument to control the size of the torsion, but it was not something that was in the original existence theorem that Tian and Yao proved. Then they were dealing with something much more general, and then they were not interested in the finer asymptotics, and so they didn't study that. But it is true that you can always make this exponentially asymptotic. But that wasn't rigorously proved until maybe if you use what Kovalev did and then use the correct type of Sobolev inequality that was proved in Hayo-Hines' thesis, then you could make it work. Alternatively, you can give the whole proof in maybe 4 pages by building in exponential decay right from the beginning. So that's the approach that this short paper with Hein and Nordstrom does.
Why do you use the Fano or Fano assumption, and not only the fact that you have a pair of text and an anti-canonical advisor, which is a
Yeah, so we also need at some stage, so I didn't really say, so we need to understand which K3s we're seeing as anti-canonical divisors. So in the semi-Fano case, in the Fano case, then just from the Lefschetz hyperplane theorem, then you would know that the Picard lattice of your Fano sits inside of the Picard lattice of your K3. In general, that's not true for a weak Fano, that map is no longer injective. It's still true for semi-Fano, and this uses this, Cataldo, or so it's a left line bundle, so you still have this Lefschetz theorem. So that tells me that tells me, well, if I see this particular if I say this K3 inside of this weak Fano or semi-Fano, then it always has to contain such a thing, such a lattice. So then I study the moduli of those lattice polarized K3s, and then what I need to know really is that I get a open dense set of such things. So if I could guarantee that, then this whole thing would work. So the semi-Fano is a convenient way to say this always works. And G2 geometers don't usually want to hear more about the algebraic geometry. But it should work. If in practice I could take a given weak Fano and try and figure out what the kernel of that map was and understand which K3s I really get, and
there are no other questions, let's thank our speaker again.